Now that we're in Desmos, let's see what we have here. So we have a function f of x that's been graphed, and you can see it's this cubic here graphed in red. And if we were to graph its derivative, let's see what that would look like. So it's this parabola. And the point I'm trying to make here is that there is, of course, a relationship between a function and its derivative, but not very often do their graphs look similar, right? Here, the graphs are very different. And if we were to say, look at y equals x squared and its derivative, let's maybe just do that. Well, we have x squared there in red, and then its derivative is just a line, okay, right? So their graphs don't have to look like each other, and again, most of the time they don't. But when we look at exponential functions, something kind of interesting starts to happen. Let's maybe try, maybe 4 to the x to begin with. Okay, so 4 to the x is graphed here in red, and then here's its derivative in blue. Okay, they honestly don't look very different. And even if I zoom out, they're pretty similar, aren't they? Let's maybe leave it just like this here. Now let's see what happens if we maybe move this down a little bit. Let's maybe try and do, say, 3.5. I don't know if you can tell, but the lines did get a little bit closer. And let's try and move down to 3. The lines are even closer, aren't they? And then let's say we move to, how about 2.9? They got closer. And let's try maybe 2.7. They are different, but you can barely tell. If I zoom in here enough, you can see that these are different lines. Let's change this a little bit more. So if you don't know this number already, or maybe haven't heard of it, if you type in just e to the 1 in your calculator, okay, you will get something that's about 2.7. Okay. And in fact, e is the number that when you take its derivative, I should be a little bit more specific about how I word that. So e is the number that when you take the derivative of it to the x, the exact same function is the result. Okay. So if I change this 2.7 to be e here, and I zoom in, you only see one graph, right? And if I zoom back out, just so you can be sure, right, the graph of e to the x and its derivative are the same. And so what this means is the derivative of e to the x is actually just e to the x. Now that we're back into OneNote here, let's write down what we just found. And what we found is that the derivative with respect to x of e to the x is just e to the x. And we'll do an example that involves e to the x here in a minute, but I want to talk about one more concept, which is the first derivative, second derivative, third derivative, so really higher order derivatives. Let's take a look at our first derivative. We know what the notation one for this already looks like. F prime of x, or df dx. Right? If we're talking about, of course, the derivative with respect to x of the function f of x. Okay. Now, if we were to take a second derivative, the notation is f double prime of x. And if we were to write it in this df dx notation here, it would actually look like d squared f over dx squared. And if you're looking for some motivation why somebody might choose to write it in this fashion, okay, well, it comes from the fact that if we are actually taking the second derivative, that means that we're taking the derivative of the derivative. Okay. So in notation, that would kind of look like this. And now you can see the similarities between these two, why somebody might want to use a shorthand for this. Okay. Let's get another one in here. Then we'll have f triple prime. Actually, I'm going to write that in a little bit smaller. There we go. And you could continue to use this notation. You could do the d cubed f over dx cubed. And then if we were to take the fourth derivative, at this point it is common to switch our convention for the order of the derivative. So rather than writing in these apostrophes, right, the primes, people will write, here we go, I'll write a little 4 in parentheses here. Okay. And it has to be in those, without those parentheses, it would mean that we were raising maybe the function to the 4th power. But in those parentheses, that tells us we're taking the 4th derivative. Okay. And if we were to take a 5th derivative, it would look pretty similar. Now, you might be wondering why we might take higher order derivatives. Okay. We will find that being able to look at the second derivative will tell us a little bit about the shape of the function. And it'll help us in the next chapter solve problems where our goal is to either maximize or minimize a function. Okay. What else here? We actually have one that we've already looked at. Okay, so this is just a little side note here, but you might remember that if you have a position function, that if you take its first derivative, that gives you the velocity function. And you might also remember if you take the derivative of the velocity function, you get the acceleration function. So in other words, the second derivative of the position function will give you the acceleration function. So we've already worked with this as an application. And when some of you maybe make it into Calc 3, there will be a formula that we'll use to approximate air with some new concept, and it'll have higher order derivatives in the formula. And these are just a few of the applications for higher order derivatives. There will be more. Let's go ahead and try out an example. So here we just have f of x equals x cubed plus sine of x plus 2e to the x minus 5. Okay, and we're going to take its first derivative, second derivative, and third derivative, just as some practice, see how this works. So let's start off here with f prime of x. Well, if we take its derivative, or how about we just take the derivative of this piece first, we'll get 3x squared using the power rule. Then we know that the derivative of sine of x is cosine of x. And then we have to differentiate 2 times e to the x. Okay. And I just want to remind you, when you are differentiating a constant times a function, right, you can just differentiate the function and then multiply by the constant. So the derivative of e to the x we just found is e to the x. So we're just going to wind up with 2 times e to the x. So the exact same thing, plus 2e to the x. And then the derivative of a constant, the very last part we have, the derivative of negative 5, that's just going to be 0. So I'm not even going to write anything here. Okay. So there's our first derivative. Now if we want to find the second derivative, we just take the derivative of the first derivative. So f double prime of x. If I use my power rule, we'll get 6 times x. The derivative of cosine is minus sine of x. And the derivative of 2e to the x is, again, 2e to the x. And then we have one more derivative we can take, f triple prime of x. So the derivative, you might remember, of just x is 1. So we have 6 times 1 here, which is 6. The derivative of sine is cosine, so we have minus cosine of x. And then plus the derivative of 2e to the x, which is, again, 2e to the x. And that's all that's going on here.